Okay, thank you very much, Martin and the organizers for inviting me. Um, so good morning, everyone. It's still morning, so we're close to noon. I hope that you can stick around for another 20-25 minutes for this last presentation. Try not to keep you thinking too much about lunch. In any case, my name is Tom van Gerven. I'm a professor at the University of Leuven in Belgium, and I'm also the chair of the Working Party on Process Intensification under the umbrella of the EFCE. And I'd like to talk about the relationship between process intensification and process electrification. It's been already mentioned a number of times in the previous presentations, so I think there's a nice connection between this presentation and the previous ones. A number of introductory slides. I won't dwell too long on them. You have seen other numbers or more recent numbers perhaps before. But basically what I think everybody realizes is that chemical industry and other related sectors are very energy intensive. For example, in Germany, 70% of the industrial energy consumption is consumed by these energy intensive industries, and the chemical industry is certainly a part of these energy intensive industries. Worldwide, if you exclude electricity usage, chemical industry produces 10 to 15% of the emissions of greenhouse gases produced by mankind. And obviously, there is already quite some electricity usage in chemical industry, so that number even increases if you would count that along. And again, we've seen numbers on how the energy market changes and the energy uses change, but still predominantly fossil fuels are the energy source for energy and electricity in particular to be produced. And when we're talking about a transition towards electrification, I think it's important to stress that this is of course only desired when the electricity that is going to be used is generated from renewable energy sources. And still this is something that is currently maybe not lagging behind, but this is an issue, and it's already been mentioned by Sophie and Ludo as well, that this is crucial, obviously, that we need to have the sufficient supply of renewable energy sources to move towards this electrification. Now, one of the issues or aspects of renewable energy is, of course, its variability. Variability over years, over seasons, over days, over hours, which we know by now, which a lot of studies have been done on this, and it's clear that at this moment we have more or less a predictable renewable energy market. So we are able to know when energy is being used, renewable energy is being used, and when renewable energy is not being used, and when it's at that moment pretty cheap to use. At the same time, a lot of research is being done on the storage aspect, batteries and so forth, but it's clear that direct consumption, if we can apply that, is I would say, beneficial towards the use of renewable energy. One aspect that has not been mentioned yet, I think, is, and Ludo, for example, in the morning indicated that, of course, it's crucial that we have this renewable energy available. I do think, and I want to give an example later on as well, I do think that we can use this renewable energy also, or we can apply electrification in chemical industry or in industry as a way to shave electricity production, where we have the flexibility to use fossil fuel-based electricity, but also, when the price is cheap, to use renewable energy based electricity. But I will come back to that in an example later on. And in my opinion, and as a consequence, the direct use of renewable energy in industry, in chemical industry, as a way to shave electricity production will, in that sense, facilitate the development of more renewable energy, as it will allow to increase the portfolio of renewable energy to be used. There's a lot of predictions and studies on how the prices look like of renewable energy. This is a graph from a Swedish report, but what you clearly see here is that there are opportunities for cheap renewable energy. For example, in this graph, it shows that 20% of the time there is, in the tomorrow's price curve, at least in the red curve, there is a expectation that 20% of the time electricity will be cheaper than what it is today if we move to renewable energy sources. And this is an opportunity also for industry and chemical industry. Now, how do we see electrification? I like this kind of picture because it shows how or what are the aspects of moving towards electrification of the chemical plants. There's of course electricity needed or could be applied for process instrumentation and control. This is, I would say, pretty normal that you're using electricity there. It's also about green electricity generation. There is, we need to think about storage, and it's going to be region dependent. What I would like to focus here on this or in this presentation is the electricity-based processing methods, because I think that will be the majority of the energy to be used in a chemical, or the electricity to be used in a chemical plant if we go to electrification. We need to be aware that electricity-based processes are not new. Yeah? In several sectors, and I just give two here, electricity has been used for many decades in chemical processes. For example, oil recovery processes, but also steel production, where the electric arc furnace technology is using electrical arcs, electrodes, to produce arcs and to melt the steel. And we've seen in the, I think it was in the presentation of Sophie Wilmet, that there's different ways to use electricity, different definitions as well, direct use, indirect use. You could, I think, equalize indirect use of electricity with the power to heat, where you're using electricity to generate or upgrade heat, whereas the direct use of electricity is then what we consider to be power to gas or power to chemicals, where we immediately use the electricity to activate chemical reactions. And electrolysis, electrochemistry, is one of the leading technologies there in the power to gas, power to chemicals transition. And what you see there is indeed that this is a kind of a maturity curve, a graph, or a maturity map of different technologies. You see on the right-hand side the technologies within electrification that are more considered to be more mature. Yeah, these are technologies related to power to heat, the indirect technologies, and also this electrochemistry of chlorine production, ammonia production. These are the well-known examples which have grown into maturity or into a relative maturity already by now. What we do see is that the power to chemicals route is kind of slower in the uptake, or is it still in the research phase, in the design phase, and so my expectation is that we will see much more examples from that perspective within the next years or decades, and eventually will be taken up in the chemical industry as well. Again, here another way to show this. This is coming from a report from the Dutch process industry, how they see the electrification And what you see there again is mostly this indirect use, electricity for heating, some direct uses, but most of them are related to electrochemical process, electrolysis, electrosynthesis, and so forth. Now, how does process intensification now come into the picture? Well, this is a scheme that some of you might have seen before, where we kind of define or outline what process intensification is. There's different principles, different approaches, and this can be done at different scales. What I want to focus on is the approach of energy, because in my opinion, this is where there is clearly the overlap with the electrification of the chemical plant. The energy that process intensification wants to take into account or wants to use to intensify processes can be done in different ways. One of the ways that you could think of is direct energy transfer to molecules. And again, electrochemistry comes to mind, but there's other technology as well. I guess all of you remember this kind of graph where you see how reactants move to products in terms of the potential energy along the reaction progress. Different energy sources can help to overcome, for example, this transition state. Electrochemistry, but also light, so photochemistry, can help to activate chemical reactions. Microwaves are able to heat selectively certain molecules, which then would hopefully be the reactants and would react to a certain product. There's also a bit more indirect effects in the sense that it's not activating the reaction itself, the chemical reaction itself, but electrical fields, laser fields, magnetic fields are known to, for example, control the orientation of molecules. And by this orientation of molecules, they can have an effect on the effectivity of the collisions between reactants and therefore make more effective, make more efficient the chemical reaction taking place. So I would argue that there is not only something like power to chemicals, where we use the power, the electricity, to directly activate the chemical reaction itself, but there's also something like power to process. We can use electricity to control or to make more efficient the chemical reaction itself. And this is also shown with this slide where, on a general perspective, there's many studies, many examples where people have shown that different fields, energy fields, magnetic, electrical, acoustical, flow, centrifugal fields, and so forth, allow to improve transport phenomena, mass transfer, heat transfer, momentum transfer, which again is not acting upon the chemical reaction itself, but it's acting upon the transport phenomenon, the kinetics of the reactions. And so this is certainly something not to be forgotten, and this is also a way to look at the electrification of the chemical industry. So again, this would be, in my opinion, a power to enable the process, not necessarily the chemical reaction itself. And so in process intensification, we're looking at different energy fields. Again, I've mentioned them already quite some times now: electrical fields, magnetic fields, microwaves and lights as the electromagnetic fields, sound fields, flow fields, centrifugal fields. And all of these energy fields are actually supplied by electricity or activated by electricity. So if we're using this, or if we're trying to find ways to use these energy fields, we're actually working in the field of electrification. Just as an example of this electrification by centrifugal fields, something that has been taken up already quite some time in industry is rotating packet beds. Another example is spitting disk reactors, but this example is rotating packet beds for the hypochlorite synthesis, where basically we're using a rotating system where the bed is rotating. You see that there's two, let me take my pointer here. There's two places or two positions where the reactants are injected. This is the chlorine being injected from the side, the sodium hydroxide being injected from the shaft of the rotor. And the two reactants are basically mixing very intensively at the location where they meet in the centrifugal field. Which allows you to have a very intimate contact, very fast reaction, but also at the same time immediately separate out the two reaction products, which is the hypochlorite on the one hand and the sodium chloride on the other hand. And this is beneficial in this case because otherwise, if you keep those two reaction products together, you will have side reactions which will deteriorate your product. So this is an example where basically the rotation by a motor is generating the intensification by imposing a centrifugal field with the for the contact between the reactants and for the separation of the reaction products. Just to show that this has been taken up in industry, the left-hand picture shows the old process, which was a big scrubber, which has been replaced by 3 of these rotating packet bed systems. And for example, the yield has increased from 80% to about 95%, with lots of other benefits, equipment size, reduction of stripping gas, reduction of byproducts, and so forth, for the same processing capacity. So that's important to stress. It's a fair comparison at that, on that level. This was an example really already taken up in industry. I want to give you a couple of other examples which are really in the research phase at this moment. There are some examples for synthesis of products. For example, there's a running project, the Simplify project at this moment at the SPIRE program, which is based on previous projects where, for example, this left-hand graph, microwaves are being used to enhance reactive extrusion of polymers. The idea there is that in an extruder, you have heating, you have conventional heating, thermal heating, but you see here at a very short or small location, there is additionally to the thermal heating, there is also microwave heating. And this allows you to increase the conversion from 62% to 80%. Molecular weight has been increased from 10 to 50%. And this brings me back to the previous points that was made, or that I wanted to make, on the kind of the additionality of the electricity-based energy. Industry would be able to use electricity at the moment that the prices are cheap to temporarily use, for example, microwaves to produce another grade of this polymer, right? A grade with a higher molecular weight. And this company can do that as long as the price is cheap. And so this means that you have a kind of a flexibility, you're building a kind of flexibility between conventional heating and this electricity-based microwave heating, which allows you to diversify your portfolio of products and at the same time produce at a cheaper price. The right-hand example is an example where we've been using ultrasounds to assist reactive crystallization. What you see is here the conventional crystallization curve, and this is the one where we've applied ultrasound, and you see that the synthesis rate has increased by 30%. Ultrasound can also be used for agglomeration. In that sense, it can also be used when electricity is cheap, that you use ultrasound as an alternative method to deagglomerate certain products. Some examples from, again, from research on separators: ultrasound-assisted solvent extraction on the left-hand side, solvent extraction in batch for a particular system showed this curve, where you had a certain time needed to reach 80% yield. If you move to a continuous system, a flow system, you could increase your rate by 2.5, because this is now the curve. And then if you apply ultrasound, you could even further increase the kinetics of the extraction and of the reaction in order to come to this time period needed to reach, what is it, 75–80% of yield. In total, by moving from a silent batch application of solvent extraction to a sonicated continuous form of solvent extraction, we've been able to show that there's an increase, a rate increase of 20 times, which is quite substantial. Another example, last example here is where, an example where we've been using light as a way to separate rare earth metals from each other, europium from yttrium. This is the yttrium, which is not affected by the light, whereas europium is reduced from trivalent to divalent and then can precipitate with sulfates, thus removing it from the liquid system. And I want to stress here, this is partially photochemistry, yeah, in the sense that we're using the light to activate the reaction, the reduction reaction from europium trivalent to divalent. But we're also looking here at, this is basically used, or we're using here LED light sources. We're also looking at the efficiency of the light irradiation. So we're moving from, for example, the not very effective mercury lamps to the possibly much more efficient LED lamps. So in this case, we were able to show that there's a 2 times increase of photochemical space-time yield by moving from this mercury lamp to LED. Okay, I just want to make another point here, which is the point that I believe that energy forms, and a lot of these again are electricity-based, enable the transition to flow, enable the transition to, for example, to the modularity or the modular processes that we've seen before. Basically, my argument is energy waves and small-scale flow are partners in crime. Waves like miniaturization, because a lot of these waves, photo, light, microwaves, ultrasound, and so forth, have a limited penetration depth. So the smaller the distance they have to travel in the liquid, the less decay, the more effective you can use them. On the other hand, miniaturizations also like waves, because of course, if you have these small-scale tubular systems, you don't want to put extra baffles in these systems to increase, for example, mixing. And their waves are these non-contact activated actuators. They can apply, or they can pursue mixing and activation without really putting extra barriers, physical barriers, in the flow system. Obviously, in micro reactors, one of the big problems is the problem to work with solid materials, solid catalysts, or crystals that are being formed. This is I guess many of you know the report of Lonza 15 years ago, where they kind of evaluated what microfluidics, microreactors could do, or continuous flow reactors could do for them in their reactions or in their processes. About half of their processes would benefit theoretically from a continuous process, but more than half of this half, and this is this part here, 63% of those reactions that could benefit theoretically had solids in the process, and which is then presenting a problem for these microreactors. And again, and so to make my point of energy forms as enablers for the transition to micro or milliflow reactors, acoustics could be used, sound could be used to avoid or postpone this clogging by solid materials in micro or millireactors. This is here an example where crystallization is taking place in a tubular reactor of limited width, without ultrasound or without sounds. If you put on the sound, if you turn on the sound, you see with a standing sound wave, you're able to concentrate the solids in the middle of the tube so as to have less solids close to the wall of the tube and less deposition of the solids on the tube wall, hence reducing clogging or postponing clogging. So as a final slide here, my take-home message is, first of all, power to chemicals can mean different things. It can mean direct use of electricity to run the chemistry, but it can also mean the use of electricity to run the process, to activate transfer phenomena. The chemistry side goes beyond electrochemistry. We see a surge of photochemistry in research, looking also at these new, effective, more efficient light sources. And the process side, obviously, in my opinion, should not be forgotten. The fact that these electricity-based energy forms can help in transport phenomena, mass transfer, heat transfer, mixing, and therefore can help the transition to, on the one hand, renewable energy sources by shaving, by having an additional flexibility in the use of renewable energy on the one hand, and also help in realizing the transition to continuous processes. If you want to know more about process intensification, there's a couple of nice handbooks, and you'll excuse me to advertise one of the books in which I was also co-author, which is The Fundamentals of Process Intensification, where a lot of these technologies are being described and which you can use really as a kind of startup to find about things about process intensification technologies. Thank you very much.